Imagine you run a help center with 1 million articles. A user types one question: how do I cancel my subscription? Somewhere in that pile is that right article. And the question is: how do you find it fast every single time? We'll start with the most obvious idea: read every single article. Then we'll see why keyword search is faster but breaks on synonyms. And finally, we will get to the practical answer, which is embeddings, plus a clever index called HNSW that can return relevant candidates in basically milliseconds. We'll build the idea in 6 steps: full scan, keyword search, embeddings, brute force over vectors, a nearest neighbor graph, and HNSW, the hierarchical navigable small world. Approach 1: read every single article. Open article 1, check if it answers the question, move on, then open article 2, and so on. Eventually, you reach the right one, which is end your membership today. For a small site, this works fine. But scanning a million articles costs roughly 1 million reads per query. Double the content and query gets twice as slow. The work grows with the collection, and this does not scale. Approach 2 is keyword search. Build an inverted index, which is basically a map from each word to the articles that contain it. The user types cancel, and the index instantly returns every article that mentions cancel. This is much faster than reading everything. But there is a catch. The article that actually contains the question is titled End Your Membership Today. It does not contain the word cancel, or it does not contain the word subscription. The user typed one set of words, the article author wrote a completely different set. Keyword search misses this best answer completely. That is because synonyms exist and they break this approach. Approach 3 is embeddings. An embedding model reads every article and converts it into a vector, which is a long list of numbers, in such a way that articles with similar meaning end up near each other in space. End your membership and pause your plan land in the same neighborhood. The sourdough bread recipe, that article lands far away. The user's question is embedded into a vector too. Now search is a geometry problem. That is, find the article vectors closest to the query vector. The query lands right next to end your membership, even though the two share zero keywords, meaning bits matching. But this exposes a new problem. With 1 million article vectors, finding the closest ones is brute force again. To answer one question, we have to compute 1 million distances. Embeddings solve the meaning problem, they did not solve the speed problem. Here is the key idea: connect each article vector to its nearest neighbors. Now the vectors form a graph. Standing on one article, the edges tell you which other articles are nearby in meaning without computing distance to everything. A greedy walk through this graph can find a good answer fast. So start anywhere, let us say the sourdough recipe, look at the nearest neighbors, move to the one closest to the query, and repeat. The walk drifts away from cooking through subscription related neighbors and eventually lands at end your membership. Most of the cloud is never visited, but the flat graph can wander through local street before reaching the right region. HNSW adds hierarchy. The bottom layer holds every article with many local links. The higher layers hold fewer articles with longer links. The top layer is sparse, like a small map of highways across the whole help center. Search starts at the top. One hop covers a long distance. The algorithm drops down a layer and refines the position, then drops down again. Highway, main road, local street. This is the mental model basically. Let us run our query. How do I cancel my subscription? HNSW starts at the entry point in the top layer. It checks that point's neighbors and greedily moves to the one closer to the query in meaning space. When no neighbor in the current layer is closer, the algorithm drops down. The current best becomes the entry point for the next layer. The search continues, now with more detail. At the bottom layer, HNSW keeps a small candidate set, which is a beam of promising articles. The width of this beam is controlled by something called efSearch, which is the one knob you can tune at query time. The other two knobs are baked into the index when it is built. The first one is M, which sets how many neighbors each article keeps, and the other one is efConstruction, which sets how hard the algorithm searches while building the graph. A wider beam checks more candidates and usually returns better matches. A narrower beam is faster but may miss a slightly better one. With a healthy beam, end your membership wins. The index is built by inserting articles one at a time. For each new article, HNSW flips a biased coin with probability roughly 1 over m. The article is promoted to the next layer up. The roll repeats until it fails. So most articles live only at layer 0. A few are promoted once. Very few survive 2 or 3 rolls and reach the top. Those rare promotions become the highways the next query will travel. Three knobs matter. M controls how many neighbors each article keeps. F construction controls how hard the algorithm searches while building the graph. F search controls how hard it searches when answering a query. These knobs trade memory, build time, query speed, and recall. With wider beam, our help center is very likely to return end your membership. With a narrow beam, it sometimes misses. So it is basically a tunable compromise. If you visit a tiny fraction of the space, and still usually you can find useful nearest neighbor candidates. Putting it together, the user asks, how do I cancel my subscription? The system embeds the question. The HNSW index returns approximate nearest candidates in milliseconds. Optional filters or re ranking refine the list. And language model writes a friendly answer. The hard problem hiding inside the Help Center bot is the one we just walked through. Here's a recap. Scanning every article is correct but slow. Keyword search is fast but blind to synonyms. Embeddings turn meaning into geometry. A neighbor graph allows local navigation. Hierarchy adds shortcuts so search reaches the right region quickly. That is HNSW. Next time someone says vector search is just nearest neighbors, remember the missing part. The hard problem is not defining nearest, the hard problem is finding nearest fast enough in a million article help center for every user every second.